All right, let's start talking about the two different types of systems that we have for energy balances. We have closed systems and we have open systems. And today we're going to talk about closed systems. So when we balance closed systems, we determine whether a system is open or closed to start with by whether or not mass crosses the system boundary during the time period covered by the energy balance. So we're looking at a specific time frame that we're doing a balance on. If the system is closed, we're looking at batch systems. If the system is open, we're looking at semi-batch systems. Okay, so when we look at a closed system, no mass is crossing the boundary at any given time during the time period which we're energy balancing. So we're putting something into a system, letting it happen, and then pulling something out. Energy is going to change inside of that system and around that system, but the mass is not going to cross the boundary. That's what makes it batch. If we have a continuous system, that means mass can change as it moves through the system. And this is the common real world system we have, and that's an open system. Okay, for our closed system boundaries, when we take our general balance equation that we've been using for the full semester, we're not going to have generation or consumption of energy in that particular system. So our accumulation is going to equal the input minus the output. No mass is going to cross the boundary, but energy can be transferred across the boundary. So closed systems are defined as the fact that no mass transfers, but energy is allowed to transfer across the boundaries. And it transfers via heat and via work. Those are the only two terms in a closed system boundary that cross the boundary. Okay, so what we're going to do in this lecture is we're going to rewrite our accumulation equals input minus output. And instead of using all the variables we've learned so far, we're going to start to use our energy terms instead and come up with our energy balance equation to use. So if we write accumulation equals input minus output in terms of energy, we basically have the net energy transferred to the system, which is in minus out, is equal to the final system energy minus the initial system energy. That's effectively the way that we rewrite accumulation equals input minus output. So the net energy transferred to the system, in minus out, is equal to the final system energy minus the initial system energy. If we put that in terms of the different terms that we know are present in the closed energy balance, what we find is that the net energy transfer to the system is the heat term plus the work term. So heat and work can transfer across the boundary as terms of energy. So the net energy transfer is related to energy that moves in and out. So that means that's Q and it's W. Now, we have something within the system that's related to internal energy, kinetic energy, and potential energy inside of the system. There is an initial and a final internal energy, an initial and a final kinetic energy, and the same with potential. So the way that we write the closed system energy balance in our systems is that Q plus W, which is the net energy transferred into the system, is equal to the change in internal energy plus the change in kinetic plus the change in potential energy of the system. So whenever we have a closed system, this is the equation that you will start from in order to try and solve the problem. Okay, so this is the basic form, basically, of the first law of thermodynamics. So if you're applying the first law of thermodynamics to closed system, internal energy depends mostly on chemical composition, temperature, and the aggregate state of the system. So internal energy is related to what chemicals are there, what temperature is there. So if you have a change in temperature, it's related to internal energy, and then the phase of the system. Now, for the purposes of this semester, we are not going to cover phase changes, but there are more advanced mass balances where changes of phase can go from liquid to gas, and then there's other terminology that we have to add to these types of balances. If the system is not accelerating and there's no change in velocity in the system, then your change in kinetic energy is going to equal 0. If a system is not rising or falling, the change in potential energy, and remember it's gravitational potential energy, is going to be 0. So these are starting to show us some of the ways that we can potentially cancel terms in the closed system. So instead of now canceling generation, consumption, input, output like we have for mass balances, we're now looking for situations where we can possibly cancel terms related to the 5 energy terms that are in the balance on closed systems. Let's take that a little further. If a system and its surroundings are at the same temperature, or the system is perfectly insulated, the process is what's called adiabatic, which you may have heard if you've taken thermodynamics, and that means that the change in heat is equal to 0. If there are no moving parts, electrical currents, or radiation across the system boundary, then the amount of work done is 0. So we're going to be looking for situations where we can possibly cancel out some of these terms. Let's put this into practice with an example. Okay, a very classic energy example is to use a piston cylinder. You'll see this a lot when you get to thermodynamics. So basically what happens is we have a gas that's contained in a cylinder. We have a movable piston that moves up and down. We have an initial state where the gas is at 25 degrees Celsius. The cylinder is placed in boiling water with the piston held in a fixed position. Heat in the amount of 2 kilocalories is transferred to the gas, and then it equilibrates at 100 degrees Celsius and a higher pressure. So there is an initial step where we move from the initial phase and then we increase temperature. Okay? Once you've increased that temperature, we then have a second phase. And then the piston is then released so that it can move. The gas is going to do 100 joules of work in moving the piston to its new equilibrium position. Now the final temperature of the gas is still 100 degrees Celsius. We want to write the energy balance equation for the two different stages described in this problem, and in each case we want to solve for the unknown energy terms in the equation. So when we do this, we want to consider the system to be the cylinder. And we're going to neglect the change in potential energy of the gas as the piston moves vertically and assume that the gas behaves ideally. Okay, so a couple things before we start this problem. There are a couple things that will tell us initially some things that we can cancel. We're going to neglect the change in potential energy as the piston moves vertically. So we know that there's going to be no potential energy term. And if the gas is behaving ideally, that might tell us something else about the system as well. So let's take a look at how we would solve this problem. So it always helps to make a little bit of a drawing. We're out of the flow diagram phase of the class and we're moving into a little bit more conceptual pictures. So let's just make a drawing of what's going on in the system. The initial system is sitting here and this bar right here is representing my piston. Inside of the cylinder, which is my system, it's 25 degrees Celsius. In this initial phase to phase 1, this first phase right here to an intermediate phase, we add heat to the system. We're adding 2 kilocalories of heat to the system, and that's going to raise the temperature 100 degrees Celsius. Now, we fixed the piston in place so it's not going to move. It didn't move up or down. Then we pull this pin basically and we allow this piston to move up. As we do that, the gas is doing work on that piston. And so we have a work of negative 100 joules, and that's the final state. So phase 1 is different from phase 2, and the terms that we can cancel in each of those phases is slightly different. So let's explore that a little bit. In phase 1, if we take our closed system energy balance, we have Q, which is heat, plus W, which is work, is equal to the change of internal energy plus the change of potential energy plus the change in kinetic energy. Now, we want to think about what terms could we possibly cancel. Well, if we think about the system, there's no moving parts. We don't see anything that's going to cause there to be work in the system. So we can get rid of that work term. We know that potential energy is negligible because we were told so in our system. And then if you think about phase 1, the piston is not moving. So there is no velocity associated with that piston, so we know that there's no kinetic energy. What that means is that the heat into the system is going to equal the change in internal energy. Now the problem statement wants us to find the energy term that we don't know. We're given Q, we need to find delta U. Now they happen to be the same in this potential circumstance, but let's maybe put it into units of energy that are a little easier to use. Kilocalories aren't bad, but let's put it into joules because joules are a lot more common. So here's a couple conversions that we can use. 1 kilocalorie is equal to 1,000 calories, so we want to get this into calories because 1 joule is equal to 0.39 calories. So if we perform this calculation, our change in internal energy is going to be 8,370 joules. Okay, so that's phase 1. Let's take a look at phase 2. Let's go back to our closed system boundary. Okay, in this system, okay, it's quite possible that we have some heat loss in this system. Okay, things are happening in the system. We don't know what could happen with heat. There's nothing that tells us that we could cancel heat. We do know that the gas is doing a certain amount of work, so we have to keep the work term. Now, delta U is kind of one of the ones that gets a little confusing sometimes. Delta U gets canceled because the temperature is not changing. If the temperature is not changing, there is no change in internal energy. So many times people think temperature is always related to heat. In fact, we want to be careful because it is related to internal energy. If the internal energy changes because of a temperature change, there will be a heat change. So the heat is as a result of the change in internal energy. It's not the other way around. So if temperature doesn't change, it's U that gets canceled. Okay? Potential energy is still negligible. And in this case, it's very, very likely that the velocity is negligible in the system. Yes, it's moving, but it's not moving fast. So in this case, that's going to be as close to zero as we can imagine it would be. Okay, so in this case, we just get down to Q plus W equals 0. So Q is going to be equal to negative W, which means that Q, our heat in the second phase, is equal to 100 joules. Now, one of the things that we're going to talk about in an upcoming lecture is when is Q positive and when is W positive. Every class defines these slightly differently, so we're going to make sure that that's really well defined in our upcoming lectures. That's going to be it for a closed system energy balance kind of introduction. We'll solve more problems related to this in class.